Doctor, given your experience in the field of respiratory medicine, you would willingly vouch for the fact that inhalation devices are beyond doubt most effective in treating patients suffering from asthma. Over the years, inhalation devices have benefited your patients. Doctor, as you would know, the objective of any inhalation device is to deliver the drug directly to the lungs. Let us briefly revisit how the device actually works. Most devices break the capsule and make available a powder, also known as the drug carrier complex, which is a combined form where the drug is loaded on to the carrier particles. Since the carrier particles are too big in size to enter the lungs deep, every device must separate or deaggregate the drug from the carrier particle. In order to achieve this, the only vehicle that the device uses is inhaled air. All devices make air to move in a certain path, and since the inhaled air attains a certain velocity, it results in a pressure drop, thus resulting in deaggregation of the drug particle from the carrier particle. The separated drug or the aerosolized drug is delivered to the lungs through inhaled air. Doctor, the question that might perhaps arise in your mind would be as to why does the pressure drop, and is the pressure drop important? According to all regulating authorities, for any inhalation device to be certified, there should be at least 4 kilopascal or 4 kappa of pressure drop within the device. Now, let us closely examine why does the pressure drop. All of us are aware of Bernoulli's principle. It states that the pressure is inversely proportional to the velocity, which means that if the velocity is high, the pressure will be low, and vice versa. Some real-life examples, such as taking off or landing of an airplane, help us understand Bernoulli's principle better. When a flight is taking off, the airplane gains velocity, and just before it is taken off, the flaps below the wings come out. This offers resistance to the airflow below the wing. Since the airflow is smooth above the wing, the pressure above the wing drops. However, the pressure below the wing is more as the flaps offer resistance and reduce the velocity of airflow. This lifts the aircraft in the air. Likewise, while the aircraft is landing, the flaps above the wings come out and start offering resistance to the airflow, thus increasing the pressure above the wing and making the aircraft to land. All devices create a path along which there is high velocity and therefore low pressure. Or simply speaking, they raise the velocity in the chamber, thereby dropping the pressure in the chamber. In a drug carrier complex, there is an intrinsic pressure of the complex, which is balanced with the atmospheric pressure. The moment the pressure outside the drug carrier complex drops, it opens up. This separates the drug particle from the carrier particle. This process is also known as aerosolization. Let us examine closely the various parts of an inhalation device and the roles that they play. Air inlet point. The air inlet point in every device creates a desired path for the airflow. This airflow is responsible for the pressure drop and also for the resistance that the device offers to the airflow. Turbulence chamber. It is a space for the airflow to be created, or the pressure drop to be created, or for the deaggregation or aerosolization of the drug to happen. Mesh. As against the common perception that a mesh is a protective layer and prevents a fragment of capsule shell from entering the mouthpiece, the mesh does a very important job of moderating the velocity of air entering the mouthpiece and keeping the angular velocity close to 180 degrees. Mouthpiece. It creates a uniform velocity of each particle that is exiting the mouthpiece.